So now that we're comfortable with arithmetic sequences, it's time to move on to the second type of sequence that you need to recognize in this course, which is a geometric sequence. So most of the sequences we give you are either an arithmetic sequence or a geometric sequence. So what is a geometric sequence? We know how an arithmetic sequence is defined as. So a geometric sequence can be written as AR squared, AR cubed, and so forth and so on. So hopefully when you look at the terms of a geometric sequence, you're thinking, wait a minute, this is very similar to what you learned with exponential functions. But remember, these are discrete functions and not continuous functions. But the idea is the values are very similar in terms of the way how they're generated. Okay, so what is A? Just like last time, A is the value of the first term, and R is the common ratio, which is the ratio of any two consecutive terms in a geometric sequence. So for an arithmetic sequence, there's a common difference, but for a geometric sequence, there's a common ratio. So just like last time, we want to generate the formula for the general term of a geometric sequence. All right, so T sub n, the general term, is equal to, let's look at the pattern, A times R, and the exponent is always 1 less than the term number, right? For the second term, it's the exponents of 1, third term exponent is 2, fourth term exponent is 3. That's R to the power of n minus 1. And of course, n is a natural number. All right, so let's make use of these geometric sequences here. Let's try to make use of these formulas to find the terms, the values of the terms of the geometric sequence. So if A is 5 and R is 3, well, the first three terms could be found rather easily. I'm not even going to bother using the formula. Let's just study the A and the R value to find out the first three terms. So the first term is 5, the common ratio is 3, so the second term must be 15, and the third term must be 45. Okay, for my second sequence here, the first term is 16, and the common ratio is a quarter. So basically I'm dividing by 4. So 16 divided by 4 is 4. Divided by 4 again is 1. Okay, so there are the first three terms. All right, example 2a. Determine the number of terms in the geometric sequence. Okay, so I know a lot of students, what they do is they just play with their calculator. They just, you know what, I don't want to show you because I don't want you to do it, but they can play with their calculator and eventually just build the number 2,916, and they tell me how many terms that is. So on the test, please don't do that, because we want a systematic way, not using a calculator to find out the answer. All right, so T sub n. Okay, the nth term is equal to 4. That's the first term. The common ratio here, hopefully you see, is 3, because 12 divided by 4 is 3, 36 divided by 12 is 3, so we're multiplying by 3. All right, so that's our general, that's the formula for the general term. So I'm going to let T sub n, the general term, to be 2,916, and then solve for n. All right, divide both sides by 4, 729. So there are a few ways you can go about to solve this, okay? You could use logarithms, which we introduced back with exponential functions, or you can do what I'm about to do, okay? I'm gonna write it over here a little bigger. So 729 is equal to 3 to the power of n minus 1. Okay, so I'm gonna write it over here. 729 is equal to 3 to the power of n minus 1. So 729 is 3 to the power of 6. And if you didn't know that, you can play with your calculator. Okay, but 729 is 3 to the power of 6. Now here, you have 3 to the power of 6 and 3 to the power of n minus 1. So since the bases of the powers are the same, you can equate the exponents. Okay, so since bases are the same, you can build an equation which will solve for n. Okay, so that's one way, or I'm going to show you another way. So so from 729 equals to the power of n minus 1. You could use what we did with logarithms, right? So log base 3 of 729 equals n minus 1. You can use your calculator, or just use your knowledge of powers and know that this is 6. So either way, you'll get the same thing. Okay, you'll know that there are 7 terms in this sequence. Okay, so there are 7 terms in the sequence. Now be careful, if the common ratio is negative, you are allowed to have a negative value for the common ratio. And if it is negative, then you can't use a logarithm method because your base will be negative and the calculator will spit out error. So yeah, those are your 2 options. Use the value, or determine the value of the 10th term. Okay, so the 10th term, no problem. I have the formula. I have the power to find the value of any term I want. So this is 4 times 3 to the power of 9. Fortunately, I gotta use my calculator here. 78,732. 78,732. That's the value of the 10th term. So the third example, we have the 9th term of a geometric sequence is 40. The 12th term of the sequence is 5. What is the first term of the sequence? Alright, let's write this down. The 9th term is 40. The 12th term is 5. So I don't know what the common ratio is, but the magnitude of the ratio is between 0 and 1, because the magnitude of the terms are shrinking. It goes from 40 to 5. Okay, so there are different ways I can do this, but I think the easiest way is very similar to what we did with arithmetic sequences with the bus stop analogy. So if I have the 12th term, or if I have the 9th and the 12th, how do I get from the 9th term to the 12th term? Be careful. We're not adding by common differences anymore. I'm multiplying by the common ratio. I'm multiplying by r cubed, right? Why r cubed? Because I have to multiply by r 3 times to get to the 12th term. It's like 3 bus stops to get to the bus station. So let's see. The 12th term is 5. And the 9th term is 40. So I have a beautiful equation here. Cube root both sides. As expected, the magnitude of the common ratio is between 0 and 1. Alright, so now I can solve for the first term. Let's see. There's a lot of different ways I can do this. I can say that the first term is equal to the 9th term, and instead of multiplying by the instead of multiplying by the common ratio, what we're going to do is divide, because you want to go backwards, right? You want to go to the first term. Okay, t sub 1, you want to go backwards, so you want to divide by the common ratio 8 times. So divide by r to the power of 8. Right? So if you have the 9th term, you want to divide by the common ratio 8 times, and that will bring you to the first term. So I have the 9th term, which is 40. Half to the power of 8. Okay, let's see. 10,240. Therefore, the first term is 10,240. All right, what do we have here? In a geometric sequence, you have the 5th term, you have the 7th term. Find the formula for the general term, which means I need to know I need to know A, and I need to know the common ratio. Before I solve for the common ratio, I have the expectation that there are going to be 2 different values for the common ratio. I'll tell you how I know, okay? So this is very similar to what we just did. I can solve for the common ratio by building the relationship between the 5th term and the 7th term. So to get to the 5th, to go from the 5th to the 7th, I multiply by the common ratio 2 times. So it's r squared. So this is 46,875, 1875. oops, divide 25, of course. So be careful. R is not just positive 5. R is plus 5 or minus 5, okay? So that changes things quite a bit, because if R equals 5, then we can solve for A. A is equal to, let's say the fifth term. So the fifth term divided by the common ratio 4 times. So the fifth term is 1875 divided by 5 to the power of 4. You know what? Either way, you're gonna get the same thing. You're gonna get the same. I'll tell you how I know, but I'll do the math. It's 5 to the 4 or 625. So it's 3. Okay. If R equals negative 5, you get the same thing. Which makes sense because it's even exponent. So even though R is negative, you're still going to get the same value for A, your first term. Alright, so I'm going to write down the formulas and then I'll tell you about the logic that was taking place in the question. So how did I know there were two values of R right off the bat? So let's say, therefore, T sub n is equal to 3 times 5 to the power n minus 1. N is a natural number. Or T sub n equals 3 to the power of negative 5 to the power n minus 1. Alright, there we go. So how did I know that there are going to be two values for R? It's going to be plus 5 or minus 5. Well, because the T sub 5, that's the fifth term, and T sub 7, that's the seventh term. I know what the fifth term is. I know what the seventh term is. So basically, the common ratio could be positive or negative to fulfill these two term values, because the even terms of the sequence could be positive or negative. Nothing's forcing them to be positive. So that means I can have a common ratio of plus 5 or negative 5, and that will still get me to these values. So if I tell you, let's say, the even terms of the sequence are, even terms of a geometric sequence are positive, then maybe the odd terms are negative, but maybe they are positive. So you don't really know. I'll let you work it out. You can build some more sequences for yourself and you can see if that continues to work out, if that pattern works. But it certainly does, based on just even looking at the algebra. Okay, so that was very nice. I like that question a lot. All right, so I like example 4 a lot, and I don't like example 3 a lot. So I'll tell you why I don't like example 5 a lot. Iodine 131 has a half-life of 8 days. Write an equation to determine the amount as a percentage of the original of iodine remaining in a sample after n half-lives. So I don't really like this question because we're gonna basically model this using a discrete function, but it really works better if you model it using a continuous function, because I can have like a half-life. I can have like a quarter half-life that has passed by. But you know, since we're in the unit of discrete functions, we're gonna use a discrete function, and this was in the homework too, so that's why I put it in the sheet. Anyways, I'm not a big fan though. All right, so 5a. So the first term, you have 50%. After one half-life, is 50%, and then 25%, and then 12.5%, and then it goes on and on and on. So the equation for the amount left as a percentage is, so the first term and then the common ratio. There you go. So you could say n is a natural number because we're really treating this as a discrete function. So you know, we'll just go with the flow for this unit. All right. So I can tell you the percent of the original amount remaining after n half-lives. And we're just gonna, we're strictly forcing n to be a natural number. So I'm only gonna tell you after like 1 or 2 or 3 or 4 or 5 half-lives, and so forth and so on. All right, if the hospital receives a shipment of 200 milligrams, how much iodine will remain after 32 days? Well, 32 days is 4 half-lives. All right, so 4 half-lives, you have to find the fourth term. So the fourth term is, you can kind of figure it out. It's 6.25. All right, so there's 6.25% left. Oh, it's 6.25% of 200. I totally forgot the 200. So I could have simplified this, but you know what? We'll do it in 2 steps. Amount remaining. 200 times 6.25%, which is, let's see, 12.5 milligrams. All right, so there you go. I really would have preferred a continuous function, but it works, but only because it was 32 days. Okay, if it was, let's say 33 days, then we should really remove this restriction of n as a natural number. But the reason why I put this because we're in the unit of discrete functions and we want to focus on natural numbers. Okay, so that's geometric sequences. So hopefully now you're very familiar with arithmetic sequences and geometric sequences.